We've already looked at finding the electric field from a single point charge, and we've looked at finding the electric field from multiple point charges. What do? We just add up the electric field from each of the individual point charges, of course using vector addition, and that gives us the total electric field. What do you think is coming next? I hope you said finding the electric field from a continuous charge distribution. What would happen if we had a rod, a solid rod that had charge uniformly distributed along its length? Or what would happen if we had a disk with charge uniformly distributed over its surface? Or a sphere with charge uniformly distributed throughout its volume? Those are the questions we're going to ask. But let's start with the simplest case, just a one-dimensional charge distribution. A rod with charge distributed along its length. Just a one-dimensional charge distribution. This is our situation. We have a charged rod, total length L, and uniformly distributed along that rod is a total charge, capital Q. We'll make it positive for this example. The rod is located along the x-axis between x equals negative L over 2 and x equals positive L over 2. And we want to know the electric field a distance a above the center of the rod at x equals 0, y equals a. Now, I snuck in the words uniformly distributed when I was talking about that charge. That's important. When charge is uniformly distributed over a rod or anything, it means the charge density is constant. It has the same charge density everywhere. So if I have a rod that's 10 meters long and the charge is uniformly distributed over that rod, I cut 1 meter off of one end and 1 meter out of the middle and 1 meter off the other end, and those 1 meter lengths all have the same amount of charge, uniformly distributed or constant charge density. That doesn't have to be the case. I could take a rod and put a tiny bit of charge at one end and then a little bit more and a little bit more, and as I get out to the other end I have lots and lots of charge. In the same amount of length I had at the beginning, I have a lot more charge. The charge density would not be uniform. It would depend on the length of the rod, how far down the rod I was. We'll talk about that later. Right now, uniformly distributed, constant charge density. One of the things we do in this class, we use a similar technique over and over again. And one of the techniques is what we're about to do. So don't just memorize an answer. Really try to understand the technique and the thought process. We're going to do this for the electric field right now in this problem. And in 2 weeks, we're going to use the exact same procedure, the same thought process, the same reasoning to find the electric potential. And then in 6 or 7 weeks, we're going to use a very similar technique, a similar thought process in finding the magnetic field from a current carrying wire. So we do sort of the same process over and over again. And if you don't get it down now, you're just going to get into more and more trouble as we go on. Really try to understand why we're doing things and what the thought process is. So we want to know the electric field from this continuous charge distribution. And one thing we can do the electric field from a point charge. So what would happen if we pick a little tiny chunk? I'll use red. A little tiny chunk of this rod, a little piece of it. And there's just a little bit of charge in that chunk. It's really, really small. And because it's really, really small, it's almost like a point charge. We can approximate it as a point charge. And we know that a point charge would produce an electric field at our point of interest, x equals 0, y equals a. This little red chunk, I should call it dq, because it's a little tiny chunk of the whole charge, would produce an electric field that points in this direction. We'll call that dE, because that's just a little tiny portion of the total electric field at that location. We have to ask ourselves, what is dE? Well, it's the electric field due to something that we are approximating as a point charge. So we know that dE, the electric field due to that little tiny chunk, is equal to K times the amount of charge, which I'm calling dQ, over the distance squared, right? Because the electric field from a point charge is K Q over R squared. K, the amount of charge, which we're calling dQ, some little tiny chunk of our total charge, and R squared. What is R squared? R is the distance from our charge, dQ, to our point of interest, the place where we want to know what the electric field is. So this is R. I'll do it in green. That distance is R. It's the hypotenuse, if you will, of this triangle right here. We know that this little tiny chunk, dQ, produces an electric field given by this equation. But we want to know what's the total electric field due to all the little dQs along this charged rod. What do we have to do? We have to add them up. But we can't just add them up because electric field is a vector quantity. So what do we have to do first? Components. Because the electric field is a vector quantity, if we want to add up different electric fields, we can only add them if they're pointing in the same direction. We must use vector components. So we have to break this up into an x component and a y component. Let's take a look at that. Here's our vector, dE. We want our x component to point in this direction. And I'll use blue for my y component. We want that to point in this direction. So we need an angle. Doesn't matter what angle you pick. Probably the one that makes the most sense is this one right here. Call that theta. And if that angle is theta, then so is this one. And now we can break these up. The y component is going to be dE times the cosine of theta. And the x component is going to be dE times the sine of theta, right? That would give us this part right here, the opposite part, which is what we want. So this is the hypotenuse times the sine of theta. And this one is the hypotenuse times the cosine of theta. Take a look at that. Make sure you convince yourself that that's correct. If you have any questions, be sure to ask and get it straightened out. Let's take a look at what we've got here. Let's plug in what we know for dE. This is going to be dE, which we know is just K dQ over R squared times sine theta. And this one is K dQ over R squared times cosine theta. We know we're going to integrate, right? Integration is just adding up a whole bunch of things. We're going to integrate this to get the total electric field. But we've got a theta, we've got an R, we've got a dQ. What's that? How do you integrate that? We've got a lot of stuff going on here. Let's go through them one thing at a time and talk about how we are going to set this up. It ends up being a single integral. How do we know that? How do we know it's going to be a single integral? Because it's a one-dimensional charge distribution. And what are we integrating over? The charge distribution. We're adding up all the little dQs that are contributing to the electric field. So we're going to integrate over that line of charge, which means we're just doing a one dimensional object and a single integral. If we had a sheet of charge, like maybe a disk, a flat disk that had charge over it, and we're trying to find the electric field at some point, maybe above the disk, we'd have to do a double integral. We'd have to add up every little bit of charge, and it's a two-dimensional charge distribution, so that becomes a double integral. What if we had a sphere uniformly charged throughout its volume, and we wanted to find the electric field at some point outside the sphere? We would have to do a triple integral, because we'd have to add up all the little dq's, and we'd have to go in the x, y, and z orientation to get all of them. It would be a triple integral. In this case, single integral, we should be able to get it down to one variable. I always start with dq. Let's try to figure out what dq is, and then we'll move on to other things, theta, x, r, y, whatever we've got. But start with dq. We want to know, what is dq? How much charge is there in this little chunk that we're calling dq? That's what we're trying to figure out. If this little chunk is just a piece of a rod, it has some length to it, and we're going to call that dx in this case, because it's lying along the x-axis, right? Some little tiny length. And we want to know how much charge is in that little tiny length. Well, let me ask you this question. If I gave you a big long rope, and I said, I want to know how much a little section in the middle weighs, and you can't cut my rope, what would you do? You'd take the whole rope and you would weigh it. And you'd take the whole rope and you'd measure the length, and you'd figure out the density. And then you'd multiply that by that little length I'm interested in the center, and you'd tell me how much it weighs. You're going to do the same thing here. We're going to take that whole rod, and it has charge Q, capital Q. We're going to divide it by the length L, because we know the charge is uniformly distributed over the length. So now we have the density. And we multiply the density by our length of our little element, dx, and that tells us what dq is. Let's write it out as an equation. So our charge, dq, the amount of charge in this little chunk, is equal to the charge density multiplied by the length of that little chunk. In this case, we're calling it dx. For charge density, we use the symbol lambda for a one-dimensional charge distribution. In general, we use s for arc length, or ds for some small length element. In this case, it's going to be dx. If we have uniform charge density, which we do in this case, then lambda is equal to the total charge over the total length. So what do we get for dq? Let's take a minute to talk about charge density. In our case, we had a one-dimensional charge distribution. So for a one-dimensional charge distribution, our charge density, if it's uniformly distributed, will be the total charge over the total length. So the units for lambda will be coulombs per meter. And our dq will always be lambda times some length element ds. And that's true even if lambda is not uniform. dq is always lambda ds for a one-dimensional charge distribution. If lambda is uniform, then dq is q over L ds. For a two-dimensional charge distribution, that means that the charge is spread out over a surface. It could be a thin sheet like a wall. It could be a disk, a flat disk. Charge is spread out over two dimensions, a surface. We use a different symbol for charge density. I'm not sure why. Maybe because the units are different. But we use a different symbol. We use sigma. And sigma is going to be the total charge over the area if the charge is uniformly distributed. That means it has units of coulombs per square meter. And what would our dq be? It would be sigma times dA, our area element, which means it's a double integral. We're integrating over area. For a three-dimensional charge distribution, that means the charge is distributed through the volume of some shape. Maybe it's a sphere, maybe it's a cube, but the charge is distributed through volume. We use rho for our charge density symbol, and that would be the total charge over the total volume if the charge was uniformly distributed, which means the units are coulombs per meter cubed, and rho dV would be our dq, and so our volume element, of course, means we have a triple integral to do there. Hopefully this looks familiar from mechanics. You did center of mass and calculated the center of mass of an odd-shaped object given some density distribution. We used very similar techniques there. For the purposes of my class, we will only do one-dimensional charge distribution, only single integrals. But once you get the techniques down for solving those problems, solving the problem where your charge is spread over a surface or a charge spread over a volume is not that much more difficult. You're just doing a second integral or a third integral. Now this is for using this technique. We will learn techniques for finding charge distributions over areas and volumes, but that's a different technique. As far as integrating double integrals, triple integrals, we won't do that in this class. Just single integration. And so for this technique, that limits us to one-dimensional charge distributions. And next week, we'll learn a technique for finding electric fields from two-dimensional and three-dimensional charge distributions. That's called Gauss's law. Let's get back to our problem. This is where we left off. We figured out that dq was q over L times dx. So we're going to plug that in, and we're going to go through and solve for the x component of the electric field and for the y component of the electric field. But before we do that, let's look at the problem again. Maybe we already know one of the answers. Do we know one of the components of the electric field already? Yes, because of the symmetry of the problem. For every dq that I drew on the left side that has an electric field pointing towards the right, there's one on the right side that has an electric field pointing the other way. Because our charge distribution is symmetric, all the x components will cancel out. So there won't be any E sub x in our final answer. We will only have a y component of the electric field. So when you see something like this, you should write down right away E sub x equals 0 by symmetry. And then spend your time solving for E sub y. But I know a lot of my students love to have an answer in the back of the book to check to make sure they got something right. And in this case, we have an answer. We know the x component should be 0. When you first start doing these problems, go through and solve and make sure you get 0. We'll go through and find both, but this is what I've got so far. For dq, I'm just plugging in q over L dx. And dq is always q over L dx. Whether we're finding our x component or our y component, it's still dx over here. Because our charge distribution, we're adding up all the charges and they are on the x-axis. K is a constant, Q is a constant, L is a constant. We don't have to worry about those. We've got our dx in there. That tells us what we're integrating over, right? We're integrating over x. So we've got r's and we've got thetas. And we want to convert those into x's because we know we have a dx in our equation. So we want to get r in terms of an x. We want to get theta in terms of an x. So let's go back and look at our diagram. Our dq is located at some position on the x-axis, right? It's located at some x value. So this is x. This is x. And r is the hypotenuse of this right triangle. If we care about this right triangle here, r is the hypotenuse of that right triangle, a is one of the sides, and x is the other side. We can get r in terms of x and another constant, this lowercase a. Using this same right triangle, we can figure out what the sine of theta and the cosine of theta are in terms of x's, a's, and r's, because it's a right triangle. Theta is the angle at the upper part of that triangle. So for sine theta, we would use the opposite side, x over r, and for cosine theta, we would use the adjacent side, a over r. We don't want it in terms of r, we want it in terms of x. Now, let's plug in for sine theta, cosine theta, and r in terms of x. So we have everything in terms of x's and our dx. I've gone ahead and plugged in my sine and cosine and my r. So you can see that this x squared plus a squared is just r squared. And this whole term over here, x over x squared plus a squared square root, that's my sine of theta. And this one is my cosine theta. Now we can integrate. We have our electric field broken down into components. If they're all pointing in the same direction, all pointing in the x direction, we can just add them all up to get the total field in the x direction. Same with the y direction. So what am I going to do now? I'm going to integrate. The integral of dE sub x is just e sub x. And the integral of dE sub y is just e sub y. So I can write that as e sub x and e sub y. And the right side of the equation, I can simplify and combine some terms. I've got an x squared plus a squared multiplied by the square root of x squared plus a squared in my denominator. So those combine to be x squared plus a squared to the 3/2 power. And the only thing that's left is the limits of integration. What am I integrating over? The charge distribution. I'm adding up every little element of charge along my rod. So I'm integrating from negative L over 2, right? I could have charge out here. I could have charge here, here, here. I could have charge everywhere all the way up to x equals L over 2. So my limits of integration are negative L over 2 to positive L over 2. Let's do our x component first. From an integral table, the back of the textbook probably has an integral table. You could look up some integrals like this. The formula sheet has it. There are a number of different sources for integral tables, but if you could look this one up, there's our answer, and we end up with and we end up with 0, which is what we expected. It's nice when you have the answer, go ahead and solve the problem anyway. Make sure you get the same answer. Now let's take a look at the y component. So here's our integral we're trying to solve. And right below it, I have the result from an integral table. And there we have our result. Now we have to figure out the direction, because these integrals only give you the magnitude of the electric field at that location. We know that this rod is positively charged, so the electric field will point away from the positive charge or in the positive y direction. So our electric field in the y direction, y hat or j hat unit vector, to show that this points in the positive direction.